You're standing on a steel platform the size of a football field. The ocean is 5,000 feet below you. The nearest city is 200 miles away. A storm is rolling in, waves hitting 30 feet high, and the whole structure you're standing on is floating. And somewhere beneath your feet, a drill is boring through solid rock, miles of it, looking for a pocket of oil that formed 50 million years ago. This is not science fiction. This is Tuesday. For about 1.7 million people who work on oil rigs around the world. We use oil every single day, in our cars, in our plastics, in the fuel that flies our planes. But almost nobody actually knows how it gets out of the ground. Because the engineering required to do that, it's genuinely one of the most complex and brutal feats of human construction on the planet. In this video, we're going to break it all down. We'll go through how oil rigs actually work, what the drilling process looks like from top to bottom, how these structures survive in the open ocean, and what happens when it all goes catastrophically wrong. By the end of this, you'll never look at a gas station the same way again. When most people picture an oil rig, they imagine a stationary tower stuck in the ocean, kinda like a lighthouse. And honestly, that's not totally wrong, but it's not the full picture either. The word rig actually refers to the drilling equipment, the machinery used to bore a hole into the earth. The structure it sits on can be a lot of different things, depending on where in the world you are and how deep the water is. In shallow water, say less than 500 feet, you've got fixed platforms. These are steel structures that are literally bolted to the seafloor. They're anchored, permanent. Some of them have been sitting out there for 50 years. But once you get into deeper water, fixed platforms stop making sense. You can't bolt something to a seafloor that's a mile down. That's where things get interesting, and we'll come back to that later. For now, let's talk about what's happening on the rig itself. Every oil rig, regardless of what it's sitting on, has the same core components. But before we go top to bottom, let's address the thing that should already be bothering you. How does something this massive even float? A large offshore rig can weigh anywhere from 30,000 to 60,000 tons. That's not a typo. And yet it sits on the surface of the ocean like it belongs there. The answer is the same principle that keeps a steel cargo ship afloat: displacement. The structure is shaped and hollow in the right places, so that the weight of the water it pushes aside is greater than the weight of the rig itself. The hull or the pontoons underneath the rig are essentially giant air-filled steel chambers. As long as those chambers stay intact and the geometry is right, the thing floats. But floating is the easy part. The real challenge is stability, because a rig that bobs and tilts with every wave is useless. To control that, rigs use a ballast system. Large tanks inside the hull or the pontoons can be filled with seawater or pumped out depending on what's needed. When you add water to a tank on one side, that side sits lower. Pump it out, it rises. Engineers are constantly adjusting ballast to keep the rig level, especially as equipment is moved around, as the drill string gets heavier going deeper, or as weather conditions change. It's a slow, continuous process of counterbalancing a structure that the ocean is always trying to tip over. Semi-submersible rigs take this a step further. They deliberately sink their lower pontoons deep below the waterline, sometimes 60 to 70 feet down, where wave motion is far less severe. What you see above the surface is a relatively light upper deck connected by columns to those submerged pontoons. This design dramatically reduces the amount of movement the rig experiences, which matters enormously when you have precision drilling equipment running around the clock. Now, staying level is one thing. Staying in position is another problem entirely, and we'll go deeper on that in the second half of this video. For now, just know that keeping a rig exactly where it needs to be, directly above the wellhead on the seafloor, is one of the hardest continuous engineering challenges on the entire operation. With that foundation in place, let's go through the rig itself from top to bottom. At the top, you've got the derrick. That's the tall, triangular tower you always see in pictures. It's not just for aesthetics. It's a massive crane system that holds and controls the drill string, which is the long chain of connected steel pipes that does the actual drilling. On a big offshore rig, the derrick can stand over 200 feet tall. That's about the height of a 20-story building, just sitting on top of the platform. Below the derrick, you've got the drill floor. That's where the workers operate. This is one of the most dangerous places on the rig. Heavy machinery moving fast, under enormous pressure, in all weather conditions. Then you've got the drill string itself. Think of it as a massive mechanical spine running from the surface all the way down to the drill bit. It's made of sections of heavy steel pipe, each about 30 feet long, screwed together one by one as the hole gets deeper. A deep well might use over 30,000 feet of pipe. That's nearly 6 miles of steel, hanging under its own weight, rotating constantly. At the very bottom of the drill string is the drill bit. These things are engineered to chew through solid rock, sandstone, limestone, sometimes granite, for days or weeks at a time. The most advanced bits are studded with synthetic diamond cutters, because when you need to cut through rock at 4 miles below the surface, you use the hardest material on Earth. How the drilling actually works. Here's something most people don't realize. The drill doesn't just spin and push down. There's a whole system working together to make it possible. As the bit rotates and grinds through rock, the drill string pumps a fluid down through its center, called drilling mud. Don't let the name fool you. This isn't just dirt and water. Drilling mud is a precisely engineered fluid mixture. First, it cools the drill bit. Cutting through rock generates enormous heat, and without the mud, the bit would overheat and fail within hours. Second, it carries the rock cuttings back up to the surface. The mud flows down through the center of the drill string, out through the bit, and then back up the outside of the drill string, carrying all the broken rock with it. On the surface, that material gets separated out and analyzed. It's a continuous, live balancing act, going on thousands of feet underground. When they hit oil, it's not like the movies. When drillers reach an oil-bearing formation, they don't just open it up. First, they case the well, meaning they lower a steel tube into the hole and cement it in place. This isolates the wellbore from the surrounding rock and groundwater. Then, they perforate the casing at the right depth, punching small holes through the steel so oil can flow in a controlled way. On top of the wellhead, at the seafloor, sits a device called the blowout preventer, or BOP. This is one of the most critical pieces of safety equipment on any rig. It's essentially a series of massive hydraulic valves that can seal off the well instantly if pressure spikes dangerously. A typical BOP stack is about 50 feet tall, weighs 300 to 400 tons, and sits on the seafloor connected to the rig above by a pipe called a riser. It is the last line of defense between a controlled well and a catastrophe. A single offshore well can produce anywhere from a few hundred to tens of thousands of barrels of oil per day. 1 barrel is 42 gallons. Do that math, and you start to understand why this industry spends billions of dollars building structures in the middle of the ocean. But how does it feel like for oil riggers to actually live there? A large offshore rig can house anywhere from 100 to 500 workers at any given time. They sleep, eat, work out, and watch TV on a steel platform in the middle of the ocean, sometimes weeks at a time without seeing land. The typical rotation is 2 weeks on, 2 weeks off. You fly out by helicopter, sometimes a 2-hour flight over open water. You work 12-hour shifts every single day you're there, and then you fly back and have 2 weeks at home. Then you do it again. The food on major rigs is actually good. Catering is taken seriously because when your workforce is stuck in the middle of the ocean with no weekends off, decent meals are one of the few things that genuinely help morale. Multiple hot meals a day, around the clock, because the rig runs in shifts, and there's always someone who just finished a 12-hour overnight. But it's still an unusual life. Loud, physically demanding, isolated, and extremely dangerous. When things go south, it gets really, really bad. We can't talk about offshore drilling and not talk about Deepwater Horizon. April 20th, 2010. The Deepwater Horizon was a semi-submersible drilling rig operating in the Gulf of Mexico, about 40 miles off the coast of Louisiana. It was drilling the Macondo well, a deepwater exploratory well in about 5,000 feet of water. On that night, a series of decisions and mechanical failures allowed a surge of natural gas to travel up the drill pipe to the surface. It ignited. The explosion killed 11 workers and injured 17 more. The rig sank 2 days later, and then the well began pouring oil into the Gulf of Mexico for 87 days. By the time it was done, an estimated 4.9 million barrels of oil had spilled, the largest marine oil spill in history. The aftermath reshaped offshore drilling regulation globally. New requirements for blowout preventer testing, well integrity verification, and emergency response capability were introduced across the industry. It's a case study that every engineer in this industry knows by heart.